Okay, binomial. Okay, we're going to talk about these repeated type experiments. A stochastic process was described as a sequence of experiments that depend on some chance element. We now consider a special type of stochastic process. Okay. A stochastic process is referred to as repeated trials such as rolling a die or cutting a deck. The experiments are identical. The experiments are independent. And when the experiments are independent, the probability of any event does not affect the probability or does not affect another event. Does not affect. Well, let me write it like this. I don't like this wording. The occurrence of any event does not affect the occurrence or probability of any other event. Of any other event. So if I roll a 1 with the die, that doesn't affect the probability or the chance that I'll get a 1 on my second roll, right? It's independent. They don't affect each other. Examples of repeated trials are tossing a coin 100 times. Each toss is identical to the previous toss, and the tosses are independent. The probability of a head just doesn't change from toss to toss. Rolling a pair of dice 20 times would be considered a repeated stochastic process. The rolls are identical and do not influence one another. Assembly line manufacturing of any product may be assumed to be repeated trials since the assembly of each product is identical and not affected by the assembly of a previous product. So here's some examples of repeated trials. Often in repeated trials, we're only interested in the occurrence of a single event. This is called a success. What's the probability an even number will be rolled? So that would be whatever you're counting or whatever you're interested in is a success. If the event does not occur, then the trial is a failure. Bernoulli trials, or a special type of stochastic process, are repeated trials in which each trial there are only two possible outcomes, success and failure. So for example, examples of successes may be the number of heads in repeated tossing of a coin, the number of double sixes in the repeated rolling of a pair of dice, the number of defective products in a manufacturing process. So even though defective doesn't sound like a success, when we're doing probability calculations, success is anything we're counting. And if we're counting defective products, that's considered a success. So each Bernoulli trial has the probability of success is P. The probability of failure is 1 minus P. The random variable x is the number of successes and n is the number of trials. So these are the formulas you need to know. Don't forget this one where the expected value of x is equal to np. And I'm going to illustrate all of that with a few examples. If you notice, I'm just going to refer you to that first chart at the beginning of the unit. Here it is, okay? So there are really 5 sections in this unit. Here are 4 of them. The first one just talked about probability distributions in general. So when your study notes are due on Thursday, so you will have these 4 sections, right? And I'll Notice the formulas for binomial. This is pretty much summarized for you, right, for your study notes. But you have to have one additional section on the probability distribution unit that we did in general, okay? A lot of people make the mistake of when they write up their study notes, they just do these 4 sections. But just remember, there's another section you have to include on your study notes. It's just probability distribution. Okay, where were we? Let's do some examples. Tabulate and graph the probability distribution for the number of heads in the tossing of a coin 5 times. Well, that's too much work. We're going to change that to 4. 2 to the 4 is 16 outcomes. I think I can get the same point across as if we do 3. Let's change that to 3 times, because 2 times 2, I think this will be sufficient. Let's change it to 3, because it's not my intention to kill this to death, like to overdo this or whatever, okay? So let's just do that. If we toss a coin 3 times, the first one can be head or tail, the second one can be head or tail, and the third one can be head or tail. So we have 8 outcomes, okay? So in this case, we have 3 heads. Here we have, so we're tabulating the probability distribution for number of heads, okay? So here we have 2 heads, 1 tail. Here we have 2 heads, 1 tail. Here we have 1 head, 2 tails. Here we have 2 heads, 1 tail, 1 head, 2 tails. We have 1 head, 1 tail. We have 1 head, 2 tails, and then we have 3 tails. Okay. So notice this is a binomial distribution because 1, trials are identical, right? I mean, we're flipping a coin, flipping a coin, flipping a coin. That's all we're doing, are identical, right? And 2, trials are independent. Probabilities do not change. Do not change. Okay? So here we have x, here we have probability of x, and here we have xpx, where we're going to calculate the expected number of heads. It didn't ask us to do that, but we're going to do that anyway. Okay? So we can either have 0 heads, 1 head, 2 head, or 3 heads, right? So notice the probability of 0 heads is 1 out of 8. Right? It's just 1 out of 8. No, because all of these are equal probable. Like this is a half, 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 a half. They're all a half. So they're all equal probable. So here we have 8 outcomes. So the probability of 0 heads is 1 over 8. But we can use our formula, probability of x equals n choose x, probability of success to the number of successes, probability of failure to the number of failures, right? So what we do is we're tossing 3 times, or out of 3 steps, right? We're choosing 0 heads, and it's 1/2 to the 3, right? Because probability of success is 1/2 to the 3, and probability of failure is 1/2, but that occurs the probability of success is 1/2, but we want 0 heads, right? And the probability of failure, where we get tails, and we're going to get 3 tails, and that is equal to 1/8. So what I'm just trying to do is get you to see the formula and relate it to this, okay? So let me just yep. 3 choose 0. So 3 choose 0 equals 1. There's only one way where we can get 0 heads. Okay? Okay? So let me just make more room here. 1. So now we want, out of 3 possible heads, we only want 1, right? This is 1/2 to the 1. Probability of our head, and we just want 1 head. Probability of failure, we want 2 failures, and that is equal to 3/8. So notice, 2 heads, 2 heads, 2 heads, the probability is 3/8, right? 1, 2. Now, the probability of 2 heads, 3 choose 2. I keep on trying to write that combination symbolism as a fraction. No, we get rid of that fraction line for some reason. 3 choose 2, 1/2 to the 2, 1/2 to we want 1 tail, right? And that is, well, there's 1, 2, 3, or 3/8, and this works out to be 3/8. And then 3 heads is 3 choose 3 is 1. There's only one way that can occur. A probability of our success, we want 3 successes. Probability of our failures, we want 0 failures, and that is equal to 1/8. We can calculate our expected value using this formula, right? Where we do the sum of x px. So you could go 0 times 1/8 plus 1 times 3/8 plus 2 times 3/8 plus 3 times 1/8. Okay. And if you were to work that out, we would get 3 divided by 8 plus 6 divided by 8 plus 3 divided by 8 1.5. But if we use the formula, expected value of x equals NP, well, we have n is the number of trials, probability of success is 1/8, probability of success is 1/2, right? Probability of a head is 1/2, and that equals 1.5. So on average, we can expect 1.5 heads. just want to show, so whether you use this formula or that formula for a binomial situation, you will get the same answer. This formula works for all the probability distributions. This is a shortcut formula, so we don't have to do that, right? N is the number of trials and P is the probability of success. Let's look at this. A pair of dice are rolled 20 times. What is the probability that double sixes are rolled exactly twice? Okay, so part A. Let X be the number of double sixes. So P, which is our probability of double sixes, or probability of double sixes, or we could say probability of success in this situation, probability of success. There's only one way you can get double sixes, that's 6, 6, and the probability of that is 1 over 36. Q is equal to not rolling a double six, so that's 1 minus 1 over 36, and that is 35 over 36. N is our number of trials, and that is 20, right? They're rolling 20 times. And what we want to find out is what's the probability X equals 2? That double sixes are rolled exactly twice. So the X is the number of successes, and that is equal to 2. So now we can put it in our formula. The probability X equals 2 is equal to 20 trials, and out of those 20 trials we want to get double sixes twice. The probability of success is 1 over 36, and that will happen twice, right? So we square it. The probability of failure is 35 over 6, and that will happen 18 times. And this is approximately 0.0883. NCR 2 times open bracket 1 divided by 36 squared times open bracket 35 divided by 36 close bracket 18.0. Does that make sense? Good? So far so good? What about the probability at least 2 double sixes are rolled? Oh boy. So here we want the probability X is greater than or equal to 2, so that's going to be the probability of 2 double sixes plus the probability of 3 plus the probability of 4 plus dot dot all the way up to the probability of 20. That's too much work, so we're just going to go 1 minus probability of 0 minus probability of 1. So it's 1 minus 20 choose 0, 1 over 36 to the 0, 35 over 36 to the 20, right? When there's 0 double sixes, there's 20 other things. Minus 20 choose 1, 1 over 36 to the 1, 35 over 36 to the 19. And we get approximately 0.105. Can I explain anything better? In a manufacturing process, it's estimated that 1% of the products are defective. So this is a manufacturing process and it's considered a binomial situation. So it's either defective or it's good, not defective. If a client places an order for 25 of the products, what is the probability that at least one of them is defective? So X is the number of defective products. All right. So notice N equals the number of trials, so that is number of trials. And that is equal to 25. The probability of success is equal to 0.001. The probability of failure is 1 minus 0.001, and that's 0.999. Okay. And we want the probability at least one of them is defective. So the probability X is greater than or equal to 1 is equal to 1 minus, well, you know that would equal to the probability of 1 plus the probability of 2 plus the, this is too much work. We're not going to do that. Well, that is 1 minus the probability of 0. So 1 minus the probability of 0 is, out of 25 trials, we want 0 successes. The probability of success to the exponent 0, we want 0 of those, right? And the probability of having good products, we want 25 of those in this case. And that is approximately 0.0247. A game consists, can I explain anything better? A game consists of rolling a pair of dice 10 times. For each sum that equals either 6, 7, or 8 on the 2 dice, you win $1. If it costs $5 to play the game, is it a fair game? Okay, we're going to need our die chart, because we want to calculate the probability of either 6, 7, or 8 on the 2 dice. So in this case, X is the sum of either 6, 7, or 8. But we're going to have to calculate those probabilities. So 1, 2, 3, 4, 5, 6. So 6, 7, or 8 is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So the probability of success is 16 over 36, right? Well, the beauty of this is we have a formula. The expected value of X is equal to NP. So N is the number of trials. The number of trials is 10. And the probability of success is 16 over 36. And that is equal to $4.44. No, it's not. Wait. So this is the number of times you expect to get a 6, 7, or 8 when you roll 10 times. Now, if you expect to get 4.4 of those, the expected winnings are $1 times 4.44, and that equals $4.44. So is it fair? No. The game is not fair because it costs $5 to play. How much should it cost in order for the game to be fair? You're right. In order for the game to be fair, it should cost $4.44. So this game is not fair. Boo-hoo. Can I answer any questions?